Hello and welcome back to Gaffy's Grinds. It's very good to have you here as usual. You know the rules by now, guys. This is video 6, so I presume you've watched video 1 to 5 first in our series on trends of the periodic table. If you haven't, then you should go and watch them first. Otherwise, some of this is not going to make sense. You know the rules by now, guys. Do try and eliminate any distractions by sticking your phone on do not disturb, close any open tabs, especially social media, because they could notify you of something and then you go off and have a look and you forget to come back. So just do close down your tabs and focus on this for a little while. And the most important thing is do the practice when I ask you to. So anything I ask you to do, you should do it. Don't frantically write to copy down everything I say or write. I will ask if I want you to take down something, if I want you to do something, and you should do those things. Otherwise, you won't learn very much at all. Okay, today we're going to be talking about another group in the table. In our previous video, we looked at group 1, and today we're going to look at group 7. So this here is group 7. As you can see, these are the elements of group 7, sometimes called group 17, but don't worry too much about that. That's just if you're including the transition metals, which if you've studied the periodic table, you should know what those are. But we normally eliminate them when we're talking about groups, and we refer to this as group 7. These are elements: fluorine, chlorine, bromine, iodine, and astatine. Group 7 is also sometimes called the halogens. Halogen. So each one of these is a halogen. So fluorine is a halogen, chlorine is a halogen, bromine is a halogen, and so on. Now, they are all non-metals. They are found on the right-hand side of the periodic table in group 7, and they are very reactive. Okay, and because of that, we find them like this. This is how we find them. So, for example, if we're looking for a sample of fluorine, we find it like this, FF. We don't normally find atoms of fluorine by themselves, single atoms like this. We find them bonded like this, two Fs together, because they're so reactive that if there's enough of them in the same space, if there's a sample of fluorine, you're going to have millions of atoms in there, and they collect into groups of 2s. Now, we've seen this before. We can also call this F2. And this here is an example of what we call a diatom. Di meaning 2, atom meaning obviously made of 2 atoms. So diatom. And they're all like this, okay? Chlorine, for example. Chlorine is Cl or Cl2. And that's another diatom. Bromine is the next one. And you guessed it, Br, or Br2. Bromine. And iodine is the same. So that is the first thing to note, is that they are all diatomic, and this is because they are very reactive. Now, more on reactivity later. Now, these are diatomic, which means they exist as molecules. So we've got, if say for example, we've got an F and an F bonded together like this. They are covalently bonded together. They are joined together by a covalent bond. So I'm going to make that a little bit more clear. Okay. F like this. Now, what type of bond is this going to be, this bond holding together? It's definitely covalent. So what I'm asking here, is this going to be polar covalent or non-polar covalent? So you should be able to tell just by looking at it, without going and looking at electronegativities or anything like that. You should be able to tell just by looking if this is going to be polar or non-polar. So I want you to speak your answer to the screen on 3. Polar or non-polar? On 3, 1, 2, 3, speak it out loud. Okay, I'm hoping that you said non-polar. And the reason how we know it so quickly that it's non-polar is that they're both the same atom. So if they're both the same atom, they both have the same electronegativity, it means neither atom has a higher affinity or greater affinity for the electrons in the pair than the other. So electrons are exactly in the middle. And with that, what type of intermolecular forces are going to hold it together? So in other words, how is this molecule going to be attracted or interact with molecules around it? So what kind of interactions will this molecule have with other fluorine molecules? And remember, it's these are called intermolecular forces. No, they're not solid lines. Intermolecular. And that's because molecular. That's because inter means between molecules. So these are not bonds. These are just what we call interactions. These are intermolecular interactions. And they're basically little tiny forces of attraction and repulsion that kind of hold molecules together in a space. And it is the strength of these intermolecular forces that determine features like melting point and boiling point. So if the intermolecular forces are very strong, if these are strong, then we have a high MP, which is melting point and boiling point. If they are weaker, then we have a lower melting point and boiling point. Now, if this is alien to you, then you really need to go and watch. Really need to go and watch the video on this in our topic on bonding. But I would imagine you would have done this before you do trends in the periodic table. My class certainly would. So, what type of forces are held together then? Are found between molecules of fluorine if they are non-polar covalent? Okay, so on 3, speak your answer to the screen. 1, 2, 3. Okay, I'm hoping that you said they would be weak van der Waals forces. The weakest form of interaction. Okay, weak van der Waals forces are the intermolecular forces that we find in between fluorine. And it's the same for all of these, because these are all diatoms, which means that the molecules are made of 2 of the same atom. So they're all going to be non-polar bonds, have a non-polar bond between them. They're all going to have weak van der Waals forces. So they're all going to have pretty low, because they have weak intermolecular forces, they're going to have pretty low melting points and boiling points. But that doesn't mean they're all the same. There's still going to be some kind of a pattern. There's still going to be some kind of a pattern going on here. So the pattern is that the strength of your van der Waals forces, so they all have van der Waals forces, the strength of your van der Waals forces, and if you've watched the video, you know what causes van der Waals forces, is the movement of the electrons inside the atoms. So as the electrons move around, they create these temporary and very short-lived, what we call temporary dipoles. So this is where electrons are whizzing around inside. If you pause at any minute in time, you can say, okay, the electron is there. It's on the right of the atom. Well, that means the right of the atom for this fraction of a second is going to be more negative than the other side of the atom, because the electron is on the right of the atom and there's no electron on the left of the atom. It's kind of hard to explain, but basically, as the electrons move, the moving electric charge, the moving negative charge, is moving around the atom and creating areas which are negative and positive. And of course, they're constantly moving and changing where they are. And they create these very weak interactions between molecules. But basically the rule is, if an atom has more electrons, or if a molecule has more electrons moving around inside it. So for example, each fluorine atom has 9 electrons each. So in a molecule of F2, there would be 18 electrons moving around. So that's like 18 electrons making temporary dipoles. Chlorine has how many electrons? I think I should know this off the top of my head, but it's group 7, so it's got 7 and 10. It's got 17 electrons. So each chlorine has 17 electrons. So in this guy here, the total amount of electrons moving around creating dipoles is 2 times 17, 34 electrons. So that's more electrons making temporary dipoles than the fluorine. So more electrons means slightly stronger van der Waals forces. And if you've got slightly stronger van der Waals forces, the result is a slightly higher melting point and boiling point, because the van der Waals forces are a little bit stronger, which makes it a little bit harder to break the forces. And if you want to boil something or to melt something, you have to break these interactions. So you have to give enough energy to break the interactions and allow the molecules to freely move about from each other. So they're separate and they can move about as a gas, for example. If you want to turn them into a gas, you have to break the interactions and allow them to free from each other. So more electrons means more van der Waals force, stronger van der Waals forces means a slightly higher melting and boiling point. So the trend here is that as we move down the group, the atoms are getting bigger and we're adding more electrons. The next one would be another 8. So that's going to be what, 26 electrons, I believe, in bromine. No, sorry, it's going to be 35 electrons in bromine. And if there's 2 of them, then that's 70 electrons whizzing around inside this molecule, creating these temporary dipoles. And that's going to make the melting point and boiling point a little bit higher, so on. Okay, so that's the general trend for melting and boiling points, and that should be revision for most of us if you've studied the chapter on bonding. So the general trend as you move down the group, the melting points and the boiling points get higher. And the reason for this is you've got more electrons creating temporary dipoles. Okay, time to do some practice now. You think you're ready to do your first little couple of questions. So what I want you to do is, first of all, I want you to pause the video and I want you to try to do these questions for me, please. Okay, so you should only be watching the video if you have tried to do those. Okay, so some of this is revision and some of it is what I just explained to you. So first question, how many electrons do the halogens have in their outer shell? Well, you might have drawn them all and figured that out, or you might have used a shortcut, which is you learn that the group, whatever group they're in, that's the number of electrons in the outer shell. So for example, the group 1 metals that we did the last day, lithium, sodium, potassium, they're all in group 1, and that what they have in common is they all have 1 electron in their outer shell. Group oxygen and sulfur, they're in group 6. They have 6 electrons in their outer shell. And these ones, fluorine, chlorine, bromine, iodine, these are all in group 7. That means they've got 7 electrons in their outer shell. Well done if you said that. So you should have written 7 and you should correct it if it's right. If not, you should fix it. What type of bond exists between the 2 atoms in a halogen? So if you take any of the halogens, like we just said, we've got a non-polar covalent. Non-polar covalent is the type of bond. It's covalent bonding and it's non-polar. If you just said covalent, that's technically right too. It is a covalent bond, but to be more specific, it's non-polar covalent. Draw an atom of chlorine. So this should be just a Bohr atom, guys. So you should have Cl in the middle. That's your nucleus. You've got 2 electrons in the first shell. You've got 8 electrons in the second shell. I'm going to draw them in pairs. It just makes it easier to keep track of them. And there is 8, and then you've got 17 altogether in bromine, or in chlorine, sorry. So you've got 2 there, 2 there, 2 there, and 1 here. So you should have 7 electrons in the outer shell. Make sure you have that done. Okay, so the parts of this, make sure you've got the chlorine nucleus, 2 in the first shell, 8 in the second shell, and 7 in the third shell. Well done, if you got that right. Draw a dot and cross diagram for Br2. Only show the valence electrons. Okay, so again, this is from bonding. You should be able to do this. We've got 2 bromine atoms, Br. We're going to draw the electrons of one of them with X's, and of the other, we're going to draw with dots. Well, first of all, they're both in group 7, so they both have 7 valence electrons. So 6 of those belong to each atom by themselves, and then they're going to have 1 sharing bond pair. They're going to have 1 bond pair. So they're going to share 1 electron each to make a bond like this. So I'm going to draw this bromine as dots, and it has 6 more of its own valence electrons like this. So each atom should have a share of 8 electrons now. So they've got 7 of their own. And then in the bond, they share another one with the other bromine. Okay, so that is, we've got a bond pair and 3 lone pairs each to make a total of 8 each. So well done if you did that. If not, add it, fix it now. If you're struggling with that, then I suggest you go back and watch bonding when we did ionic dot and cross diagrams, because again, it's really going to help to understand this stuff better. Explain why fluorine has a low melting and boiling point. Fluorine has a low melting and boiling point because it only has weak van der Waals forces. Or weak intermolecular forces. So if a substance has weak intermolecular forces, then it will have a low boiling point. If it has strong intermolecular forces, it will have a higher boiling point. If it's in between somewhere, it will be obviously a scale as you work your way up. So It has weak van der Waals forces. Out of all of the halogens, fluorine has the weakest van der Waals forces because it's got the least number of electrons moving around inside the atom to create the van der Waals forces. Okay, so that is why fluorine has a low melting and boiling point. And in fact, all of the halogens have low melting and boiling points. They're all low. Relative to other substances, these are low, but there is also a scale within them. So fluorine being the lowest, chlorine being a little bit higher, bromine being a little bit higher, but we still wouldn't describe them as high melting and boiling points. They're all low. It's just that some are lower than others. And that's to do with the number of electrons in the atom. Number 6, and this was a challenge, so hopefully we were able to answer this. So why does the boiling point increase down the group? Think about intermolecular forces and what we learned when we looked at, well, that shouldn't say polymers, that should say bonding. So I'm going to change that for the next time. Sorry, bonding. All right, so why does boiling point increase? I'm going to say BP, boiling point increases down the group as the larger atoms, and a key phrase coming up, you should have said, have more electrons. So you should definitely refer to the bigger atoms down the group having more electrons, creating stronger van der Waals forces. Van der Waals. You can call them van der Waals intermolecular forces if you want. So you can use the word keyword intermolecular in your answer because it is in the question. All right, so boiling point increases down the group as the larger atoms have more electrons, creating stronger van der Waals intermolecular forces. This increases the boiling point because it takes more energy to break or to overcome these stronger van der Waals forces. It really is that simple. People blow the idea up in their head and make that very complicated, but hopefully it makes sense there. I'm hoping that you guys are sticking with me. So boiling point increases down a group. Boiling point depends on your intermolecular forces. Van der Waals forces are very weak intermolecular forces, but you can have stronger ones than others. So more electrons means stronger van der Waals forces. Okay, now we're going to take a look at the next idea. So I'm just going to actually drag this down here. And we're going to look at the trend in reactivity. So we said that these are all reactive substances. They're like our alkali metals, they're all reactive. Now, unlike the alkali metals though, when you remember the alkali metals we said have to lose electrons to react because they all have one electron in their outer shell. For example, lithium has one electron in its outer shell, like there's its electron in its outer shell, and it has to lose the electron in order to react. Sodium also has one electron in its outer shell. Here's the one electron as an X, and it has to lose that electron if it's going to react. Potassium also has one electron, and it has to lose that electron if it's going to react. Because they have one, if they can lose that electron, then they can have a stable, and can have a full outer energy level if they can lose this one electron. So they all lose. Now the pattern, actually, sorry, before I go on, Na plus, NaX losing the electron and potassium losing the electron. We looked at the pattern, how does reactivity change down this group? And we said, well, it's all got to do with the size of the atom and the number of shells. So lithium being the smallest atom here, this electron here is closer to the nucleus of lithium than this one is to the nucleus of sodium, because the atomic radius of sodium is bigger, which means we know that the outer electron is on the extreme edge here. So if I draw it as a black dot, it's out on the edge. If I draw it as a black dot here, sorry, it's out on the edge. And if I draw it as a black dot here, it's out on the edge. Now this is obviously further from the center of the atom where the positive charge of the nucleus is trying to hold on to it. So when the nucleus or when the radius gets bigger, it gets easier to lose an electron. okay, which makes it more reactive. So that is what we call our first ionization energy. So when these atoms lose an electron, they do their first ionization. So if the first ionization energy is low, then it's really easy to lose the electron. And as we move down the group, they have a lower first ionization energy. If we look at the other side though, here at group 7, if these want to react, these have to gain an electron. So these actually have 7 electrons in their outer shell and they want to gain one. So to react, they have to receive or take an electron. Now, the easier it is to gain an electron, the more reactive they will be. So the atoms that gain an electron quickest, gain an electron easiest, those will be the most reactive. So let's look at the radius of these atoms. Well, here we've got fluorine, which is a radius of around there. Chlorine is below, so it's going to have extra shells, or an extra shell. It's going to be a bit bigger of an atom. Bromine, a bit bigger again. Iodine, you're getting the idea here, bigger again. And that'll do us. We'll just do them 4. Now, these want to gain an electron. To do this, they've got to take an electron from another atom. They've got to, so say we've got an atom that comes close and it's got an electron at its edge. And we've got an atom that comes close and it's got an electron at its edge. And here we've got another atom that comes close and it's got an electron at its edge. And here we've got another atom that comes close and it's got an electron at its edge. Now, the reason why these atoms can take an electron from this atom, is because their nucleus is able to pull the electron off the purple atoms. The nucleus has a high nuclear charge, it's got a lot of protons, and it's able to pull an electron off another atom. Now, obviously, or I'm hoping it's clear, that if the halogen atom is smaller, then that positive nucleus gets closer to the purple atom and has more of a pull on the electron of the purple atoms. Okay, so if the atoms are smaller, the halogen atoms are smaller, they are able to take electrons better. We can see this in the table of electronegativities. That kind of gives us some kind of an idea over whether negativities, it gives us some kind of an idea of how much pulling power they have, if you like to think of it like that. And electronegativities increase up the group. In other words, fluorine is the most electronegative, more than chlorine, more than bromine, more than iodine. This is because fluorine has the smallest atom and its nucleus can get close to other atoms and pull electrons off them. It also has the fewest shells of electrons to provide a screening effect. Okay, so this gives us the rule here that the reactivity, how reactive they are, how easily they gain electrons, the reactivity increases as we move up the group. So for group 7, notice this is the opposite of the alkali metals. Alkali metals got more reactive as we went down the group and the atoms got bigger. It became easier for them to lose electrons. For the halogens, they get more reactive up the group because they have to take electrons. And smaller atoms with less shells can get their nucleus closer to another atom to take an electron off it. So I just want to make sure that we remember and we're very clear on the fact that the reactivity of the halogens is the opposite to what happened for the alkali metals. The alkali metals are more reactive when the atoms get bigger and they can easier lose an electron. The halogens, however, are more reactive as the atoms are smaller and they can get closer to another atom to remove its electron. So the reactivity increases going up the group for the halogens. It's the actual opposite. Okay, so why does it increase up the group? Okay, so it increases because what are the factors then? Well, the factors are the distance, what would you say? We say atomic radius is one factor. Atomic radius. Okay, so we say smaller atoms can get closer to valence electrons of other atoms. Okay, so smaller atoms can get closer to valence electrons of other atoms, and that lets the smaller atoms remove the electrons easier. Another thing is the shielding. The shielding is the other factor, or the screening. I shouldn't say shielding because I've been using screening. Sorry, screening is another factor. So fewer shells, which of course are found in the smaller atoms, fewer shells means less screening of the nuclear charge. Okay, so for example, chlorine has an extra shell more than fluorine, and this means that the screening effect of chlorine is higher than fluorine. So screening effect of chlorine is higher than fluorine. What this means is that the nuclear pull, or the nuclear charge of chlorine trying to pull on electrons from other atoms to take them, is weaker, or is screened, as we call it, more than that of fluorine. So fluorine has one fewer shell of electrons to screen out the nuclear pull on other electrons. Okay, so these are the two factors, screening and the atomic radius. These are the factors that affect the reactivity of group 7. All right, what I would get you to do maybe is you could take down this section for me. If you want to make some notes, that would be a good thing to take down. I'll pause the video and do it now. Okay, so I'm moving on. If you need more time, keep it paused. We're going to do some practice now. Okay, so let's see how you get on with these. All right, so pause the video and do the questions that you see there now, please. Okay, pretty sure you should be able to do the first 3 based on what we just did. Number 4 is you have to write a reaction between lithium and chlorine. So it says write a symbol equation, but sometimes it helps if you write down the word equation first. Let's see how you got on with those. Okay, so first of all, explain why fluorine is more reactive than chlorine. Well, fluorine has a smaller atomic radius and less screening, or fewer shells, than chlorine. That makes it more reactive. And that's because it can get closer to other atoms, and the nuclear charge of fluorine can get closer to other atoms and help it to remove electrons from another atom. Explain why bromine is less reactive than chlorine. Well, bromine is below chlorine. That means it's got a bigger atom and more screening. So bromine has a larger atomic radius and greater screening because it's got more shells. And this means that the nucleus of bromine can't get as close to other atoms to remove their electrons. So they are less likely to take electrons, and therefore they are less reactive. Explain why potassium is more reactive than lithium. So this was jumped in or looped in with the last video stuff. So notice that we're switching to the alkali metals here. If you hadn't copied that, guys, do have a rethink. This is the alkali metals, so not the same group. So if you didn't realize that, do pause the video and fix it now. Okay, so why is potassium more reactive than lithium? Well, potassium is below lithium in group 1. Potassium has a lower first ionization energy, which means it loses electrons easier than lithium. That makes it more reactive. So potassium has a lower first ionization energy than lithium. That means it takes less energy to remove electrons from potassium than it does from lithium. Therefore, it's more reactive. It really is that simple. Now, write a symbol equation for the reaction between lithium and chlorine. Okay, I said you can help to start by the way, you should have corrected these. Make sure you actually physically correct them in red. And it can help to start with a word equation. So we're reacting lithium plus chlorine. And we're going to get, well, when we're making compounds with two elements like this, or two element compounds, we know that we drop the ending of the non-metal here, the chlorine, and we replace it with IDE, ide. So we get the substance lithium, and what will the ending be? On 3, speak your answer. 1, 2, 3. Should be lithium chloride. That's what we should have. Good. Now, lithium is a metal, and we do get just individual lithium atoms. Chlorine, if we add chlorine, exists as a diatom. So we went through that at the start of the video today. So chlorine is Cl2. Well done if you knew that. If you didn't know that, I'll give you an opportunity to pause and maybe fix it. If you had made a mistake there, if you've just written Cl there, then that would be a mistake. So do pause and fix it now. Okay, so what do we form? Well, you should have LiCl, lithium chloride. 1:1 ratio, and the reason for this is lithium is in group 1, it's got 1 electron to give away. Chlorine is in group 7, it wants to gain 1 electron. So one lithium can provide 1 electron for 1 chlorine. And that's a 1:1 ratio. They're both, that's how they would bond. They both have achieved what they wanted, which is a full outer energy level. Now, obviously, this is not balanced though. Okay, so we have a problem with balance here because we have an atom which has been destroyed, and that is one of the chlorine atoms has been destroyed. So we have to account for that over here by making 2 of this whole thing. Okay, so we have to protect the formula. We can't stick a 2 on like that. You're not allowed to do that because that changes the substance that's been made, and that's the substance that's been made is definitely LiCl. So we put a 2 in front of that. Now the chlorines are balanced, and I have messed up my lithiums. So if I can fix that by putting, well, 2 of these. So now it should be balanced. Check again, 2 lithiums, 2 lithiums, 2 chlorines, 2 chlorines. Happy days, that's balanced, well done. Right, just one more note to do. We're going to take a look at a brief look now, because we are going to look at this again in a future topic when we study something called redox. But we're just going to take a look at a specific type of reaction that the halogens do. Okay, I'm going to take a look at this chemical reaction. We're going to have a look at, we've got potassium chloride. So we've got potassium chloride, and we react it. You'll notice we've got one of the halogens in this compound. We've got chloride, so we've got chlorine in this compound. And we're going to react it with fluorine, another halogen, fluorine. And our product is going to be potassium fluoride plus chlorine. Now, I'm just going to try and represent this for us so we can see what's going on. I'm actually going to write the balanced equation first. This is what's going on here. We've got KCl, sorry, I'm just going to change back my color for a second. We've got KCl, which is potassium chloride, KCl. And we're reacting it with fluorine, F2. So it's a diatom, fluorine, diatom. And we're getting KF, potassium fluoride, plus chlorine, Cl2. Now that's not quite balanced yet, so I'm just going to balance it now. To balance it, I'm going to need, actually, you know what I'm going to do? I'm going to get you to write it down and balance it yourself. Practice balancing that equation for me. Do that now, pause the video. Okay, what you should have got, you should only be listening if you've balanced the equation. What you should have got is 2 KCl, 2 KF. Now it's balanced. Now we're just going to really quickly draw out what we have here. So say these orange atoms are potassium, and we've got orange, and this blue one is a Cl. So we've got 2 KCl's, which means I need 2 of them like this. There's a second particle of KCl like this. And I'm going to say that these bright pink ones are fluorine, F2, like this. Now, in our product, what we should notice is that over here now, I've got the orange Ks, but now they're attached in particles, or they're bonded with the Fs, like this, KF. And essentially, I've now got these free or loose two chlorines that are stuck together and they're free from the compound. So remember that this is called a compound because it's two elements combined. This is an element because it's just made of one type of atom. This is a compound because it's made of two or more types of atoms. And this is an element, chlorine. Essentially, what's happened here is that the fluorine has replaced the chlorine in the compound. So when we make a new compound over here, fluorine, the Fs, have replaced the Cls in the compound. The Cl now is the element form. And the reason why this is that the fluorine is more reactive. It's a more reactive element than the chlorines. This is less reactive. So we've got two halogens, and we've already looked at the pattern on the periodic table. Remember, up here, we said fluorine was at the top, and it has a smaller atom, so it's more reactive. Chlorine is below that, and it has a bigger atom, so it's less reactive. So chlorine is a less reactive element here, and fluorine is more reactive. So the more reactive atom replaces the less reactive atom in the compound. We call this a displacement reaction. Displacement. Okay, which is essentially replacement is taking its place. So the more reactive atom pushes out and takes the place of the less reactive atom. So you can actually look, if you learn the pattern here, that the more reactive elements are at the top of the halogens, then when they react, you will know which one would replace the other one in a reaction. Now, if I did this the opposite way around, if I started with this KF and I mixed in Cl2, if I started it the other way around, then is the chlorine going to replace the fluoride? Am I going to get a reaction there and replace the fluorine with the chlorine? The answer, of course, is no, because chlorine is the less reactive element. It's less reactive. And if it's less reactive, then it cannot replace the more reactive one. So this type of reaction, this displacement reaction, only works when you're adding a more reactive element to a compound that contains a less reactive element. All right, it really is that simple. More reactive always replaces less reactive in a compound. All right, time to do some practice. All right, so let's see. Yeah, hopefully you should be able to do that. Some of that is from bonding, guys. So again, I'm assuming you've done bonding. If you have done bonding, you should be able to do those. So I want you to pause the video and write out the answers to that, please. Okay, so you should only be watching if you have tried to do those questions. Write a word and symbol equation for the reaction between bromine and lithium iodide. Okay, so lithium iodide is going to be Li, lithium, and iodine's in group 7. So it's a 1:1 compound. Lithium's in group 1, iodine's in group 7. That matches up nicely. 1 electron given away by lithium and 1 electron taken by iodine. So lithium iodide, that's the formula. If you didn't know that, sorry, and I should do the word equation first. So lithium iodide plus, what am I reacting with it? Bromine. Like this. So plus bromine is going to be Br2. So hopefully you did that right. So what is going to happen? Well, is bromine more reactive than iodine? So go to your periodic table, check which one is higher. Well, I'm seeing that, where am I? Where's my halogens? Here they are. I'm seeing that iodine is below bromine. That means bromine is more reactive element than iodine. So is it going to replace the iodine? The answer is yes, it will. So what I end up getting is lithium, and it's not going to be iodine in there anymore. It's replaced with the bromine. So it's now going to be lithium bromide. Oh, excellent job if you got that right. Plus, well, now iodine is going to be the loose element. So it's going to be iodine now. And that's going to look like this, LiBr plus I2, because iodine is a diatom. Now, again, well done. Excellent job if you got that right. It's not fully balanced yet because I've destroyed some atoms at the moment. So I've got 2 BRs on the left and I've only got 1 on the right. So I'm going to fix that up by putting a 2 here. And I've got 2 iodines on the right and I only had 1 on the left. So I'm going to put the 2 here. And then I'm just going to count everything. 2 lithiums, 2 lithiums, 2 iodines, 2 iodines, 2 bromines, 2 bromines. Good. So there is question 1 done. So do correct it now. Hopefully you got it right. Well done if you did. And if not, fix it up for me. In the above reaction, identify the 2 elements and the 2 compounds. Okay, so I'm going to write C under the compounds and E under the elements. So lithium iodide is 2 or more elements. So this is a compound. Okay, so now I've done the first one for you. If you didn't know what to do, you might be able to finish that yourself. So pause it and finish it. Okay, you should only be watching if you've got this done. Bromine is an element, so it should be, sorry, I don't know why I'm writing an I. This should be an E element. Bromine is an element. Lithium bromide is 2 or more elements, so it's a compound. And iodine only has 1 element, so this is an element. What kind of substance, ionic or covalent, is potassium fluoride? It's a metal and non-metal, or you can use your periodic table and electronegativities to work out what type of bonding. But I know it's a metal and a non-metal. I know it's going to be question 3. Potassium fluoride is a ionic substance. So potassium fluoride is ionic. Explain why potassium fluoride has a higher melting point than fluorine. Well, potassium fluoride is ionic, and ionic substances have very strong electrostatic forces between the ions. Forces between the ions, much stronger than van der Waals forces. So that's what holds ions together in a crystal. When you have an ionic substance, you have millions of these ions in a crystal, and they're held together by electrostatic forces, which are extremely strong. This gives them very high boiling points compared to van der Waals forces in between covalent substances. Explain why iodine is less reactive than bromine. Well, iodine is further down the table, which means it has bigger atomic radius and more screening. So you should have those in your answer. Well done if you did. And explain why chlorine does not conduct electricity. So chlorine is just Cl2, remember? Cl. Well, for stuff to conduct electricity, it has to have 2 things. It has to have charged particles and it has to be able to flow. Now, chlorine is a gas. So can it flow? Well, gases definitely can flow. So we've got these gas particles which can flow around and move around. So it ticks one of the boxes for electricity. But chlorine molecules, these are, do they have a charge? Overall, no, they do not. They are neutral. Okay, there is no charge here. We haven't got one atom that's taken an electron and one atom that's lost an electron. Those are charged particles. So charged, it does not have. So explain why chlorine does not conduct electricity. Chlorine does not contain any charged atoms or ions. Does not contain any charged atoms or ions. So overall, it's a neutral compound. It's a neutral compound. It's not charged. So even though the particles can move about, they do not carry any charge and therefore they cannot conduct electricity. Again, that one's quite tricky and it's very applied. It's really applying your knowledge to see, do you know that covalent substances do not conduct electricity, ionic substances do conduct electricity. And this is obviously a covalent substance, does not conduct electricity because it has no charge. It has no ions in it, there's no charged particles. All right, guys, that's it for today's video. I hope you found it useful on the halogens. And that's pretty much the end of the road for trends in the periodic table. I hope you found it useful. Do tune in for future topics. If you found this useful, please do leave us a like and a comment below if you found that particularly good, or if you found that bad, or if you'd like me to add something else or change something up. Do let me know in the comments below, and I'll see you in the next video.